Okay, thank you very much. First of all, I would like to express my appreciation for the invitation. It's a really great pleasure and honor for me to present about the experience using co-benefit tools for projects in Asia. What I'm trying to explain today and present to you is about basically the achievements of the projects, which is the contract based on the contract between Kyushu University and IGES. And I'm serving as the principal investigator of this project, working with Dr. Zusman as the project leader and his colleagues. So the projects here include the heat-only boiler and solar energy in Mongolia, particularly in Ulaanbaatar city, and also the fish industry wastewater treatment in Indonesia. And the main goal of this development of these tools is to quantify the co-benefits in terms of the avoided pollution, avoided health case and mortality, and also to estimate the associated saving costs by improving the health impact. So we focus on emission and health impact and also local economy. Just give you the idea for developing this tool. Basically, this tool is supposed to be being used by the wide range of the scholars, wide range of the stakeholders, not only the scholars and professors or researchers, but also the people from locality, utilities, and government. So we try to make a tool as the first order screening to help the stakeholders to first to understand the meaning of the co-benefits, and then to help them to quantify the different co-benefits in terms of the reduction in air pollution and also avoided case in terms of the mortality. So when we discuss about the quantification, this is basically the technical dimension of the co-benefits tool, which deals with how much. And as the previous speakers mentioned, the institutional dimension is also very important, which deals with how come and explain the impact of policy implication. And the total co-benefit assessment, can be calculated as the product of the technical dimension and the institutional dimension. However, in developing this tool, we were able to consider only technical dimension. Because I'm talking about a tool which is supposed to be used by the wide range of the stakeholders, please allow me to explain the challenges that we faced through developing this kind of tool. If you consider the development process of the tool in different sections, like technical, different steps, like technical step, the interface and result. So the main challenge here is how to trade off the accuracy and simplicity in technical part. So we try to have the robust mathematical foundation and technical instruction for our model, but because the tool was supposed to be used by for example, general people, we try to simplify to be understandable by the different stakeholders. For the interface part, of course, user-friendliness is really important. So we try to make a tool which is accessible by the user, the user can find the different parts, connect the different parts, and for example, run the tool with the limited data, with the default data which were available in the tool, as well as considering the adaptability, which enables users to run the tool in different OS or operation system or different environment. For the result also, we had a very careful attention on not only the correctness, which is very important, but also on scalability of the result, how to upscale the result from one project to region and to even national level. So for some project we were, did it, but for some project it was really difficult. I will explain to you about the result and achievement from the different tools. When we come across the technical part of this tool, you can see the tool has 3 subsections. The first part is the scenario analysis, which the user tries to actually introduce different intervention scenarios, different measures, like, for example, improved heat-only boiler or different technology for solar power generation, or even wastewater treatment. And the main output is the avoided emissions in terms of the GHG emission and different pollutants. But to assess the impact of the pollutant exposure on the health and public health, so we need a translator in between. So we developed air pollution dispersion model based on Gaussian theory and approach to actually to convert the mass unit of the avoided emission to its concentration, particularly PM 2.5 in this assessment. And then at the last part, the health and economic benefit. For the health part, we consider the CFR, or concentration response function, to correlate the change in concentration of, for example, PM 2.5 to the public health endpoints in different diseases. So we developed the comprehensive database on relative risk function for different diseases here. So when you look at the tool, so you can see we also consider the 2 dimensions. It's not only used for the particular area, but also you can apply the result to the different regions in a country. And also we consider the definition of different technologies for each project. So, I would like to show you the different tools that we develop one by one here. I will start with the first one, the solar energy co-benefits. So you can see this is kind of the spreadsheet tool. And here we consider both power generation and thermal energy generation from the solar energy, with different categories and different types of the photovoltaic system and collectors. And here we try to calculate the hourly power and heat generation by considering a very, very detailed spherical coordinator system here, considering the detailed solar incident radiation on tilt surface in different area. And as I mentioned, the outcome from this part is avoided emission, which can be further used for the health impact assessment and economic assessment. So the solar energy tool was used in solar energy projects in Ulaanbaatar, considering 2 different purposes. The first one, how to use solar water heater to avoid or to decrease the need for using HOB, which is the heat-only boiler with very inefficient way to use energy. And the second one is how much power can be generated by photovoltaic to replace the power generated by the coal power plant here. So we focus on both scenarios, both technology here. And I just want to show you the result from one of the particular project that we consider based on the UNEP suggestion, the installation of 100 megawatt PV, and also replacing 20,000 solar collectors in the residential area in Ulaanbaatar. And then you can see the result in terms of the total electricity generation and thermal power. And you can see the impact of the huge or significant impact of this project on GHG emission reduction and PM2.5 reduction, which is further used for the public health assessment here, considering the background mortality data, and actually the concentration of PM, which was already calculated by the dispersion model. And then the tool can present the result for different diseases, as you can see here, in terms of the averted dailies, and that can be also used to calculate the healthcare cost saving and even the unemployment rate reduction in the case of for example, solar energy project in Ulaanbaatar. And so you can see the result altogether here, and tool will help the user to visualize actually the co-benefit. Here you can see the variation of the GHG emission reduction with the different pollutants as the environmental co-benefits. And all together here, in terms of the daily averted, the PM reduction, the cost saving, and GHG reduction, which gives a very nice visual, understanding about co-benefits here. So even it's possible to use the tool for the different regions. Here I want to share the result from different cities in Mongolia, and you can see the impact of environmental, meteorological parameters like here is the ambient temperature, on surface temperature of the collector, and you can see how the ambient temperature would affect even the number of dailies, or the case of avoided case of the avoided health case in the different city, and the saving associated with these avoided cases. The next tool is the heat-only boiler co-benefit tool, which is basically a simple boiler. And here what we consider the different technical parameters which is needed to calculate the overall thermal efficiency of the boiler, considering the main thermal loss in boiler, and also the different type of coal, and so the different climate condition. We consider the this 5 scenarios here, replacing the coal feeder, air preheater, the cyclone, dust removal, air feed adjustment, and moisture control. So this tool was applied to a real case study. So here you can see the problem in Ger area, which is the traditional area in Ulaanbaatar. The people here they use very low efficient stoves, as I mentioned, and the system which was suggested by Ministry of Environment is here, that you can see that the improved HOB can be used to to increase the efficiency by adding the different features, like for example adding cold storage, or as I mentioned, for example, air fuel ratio control system, or coal feeder. So what we have done, we try to quantify the resulting co-benefits or expected co-benefit from the implementation of this scenario in Ulaanbaatar. And now again, you can see the result. And if you consider the total number of HOBs in Ger area, Ulaanbaatar, then it would be around 250 HOBs. And then if we want to replace all of these HOBs with the improved one, then you can get significant reduction in GHG emission and also PM emission. And it has a very impactful effect on the public health endpoints in terms of the dailies avoided and also the saving associated with these dailies avoided. So then the last tool is the Wastewater Co-benefit assessment tool. Again, for the technology assessment, we consider the definition of 6 important wastewater treatment technology. And so here the main input data is the water quality, and the tool calculates 2 important things in this part: the avoided emissions and the COD concentration, or basically the COD removal. COD is the chemical oxygen demand, which is one of the important indicators which is used to evaluate the quality of wastewater treatment system. And then this COD concentration is used in the health impact assessment model to assess the health burden from the improving the COD concentration by adding the new technologies. So we use this tool in one of the project which was studied by the Ministry of Environment. So this is the current existing wastewater system in particularly in the food fish industry in Indonesia. So you can see basically they use anaerobic lagoon, which is very simple one. And these are the intervention scenarios which were suggested by the Ministry of Environmental Japan, like using the activated sludge system like this by aeration of the wastewater, and then or using swim bed by adding some fiber material to select the inorganic material to separate the inorganic material from water, or organic material from water. And then the last one is the USP, which is upflow anaerobic sludge blanket, which has several benefits in terms of even it can generate methane gas, which can be further used for the electricity generation in the system. And finally, the combined scenario. Again, we tested this project using our tool, and now I just want to show the result from the a comprehensive analysis for a given 35,000 meter cubic of wastewater treatment per day in the Indonesian food industry. And then you can see how the implementation of the new technology can help to reduce the GHG emission, and the other hand can help to enhance the COD removal efficiency, which is very, very important. And this is the result for all, fish industry factories in, in Indonesia, considering the 3.5 million ton of wastewater per day. And so you can see the combined scenario can bring a lot of co-benefits in terms of the, again, improving the COD and the averted dailies, which is almost 396,000, which is a huge number. And consequently, the saving and the reduction in unemployment rate. So, so here again, you can see the comparison between these three technology or these three suggested intervention scenario, and then how to visualize the result and how to have all of these co-benefits in one picture, which helps us to understand the meaning of co-benefit, the integration between different benefits, and the impact of the new intervention scenario on obtaining the co-benefits. The tool is further used in different regions, all regions in Indonesia, by collecting data about the wastewater quality and the quantity. And then here is a very nice map which shows the daily averted in different regions. As you can see, in West Java, Central Java, the impact of the implementation of new scenario is very considerable and compared to other regions, which means that this area should be considered as the main focus area for the future improvement and implementation of the wastewater treatment. Thank you very much. If you are interested in the detailed calculation, I would suggest you to refer to our recently published book together with Eric and colleagues at IGES, which covers not only the technical part, but also the scenario, different scenarios for different case study projects in Asian cities and Asia, and also introducing the new method for the co-benefit, like the social co-benefit. Thank you very much for your pay attention.